Ladies and gentlemen, good morning. We are ready for the keynote lectures of Thursday. Today we will have a double keynote lecture. The first one will be given by Bill Ellsworth and the second by Enrico Priolo. The aim of this keynote is a bit different from what we have done in these days. So we would like to have the first two speeches first and then sort of debate at the end of keynotes. So it's like usual, very nice if we can have questions for our speakers, but also it could be very important if we involve or if people in the audience is also involved actively in the discussion. So we can go to the first keynotes. It's given by Bill. Bill is a professor in the Department of Geophysics at the Stanford University, where he co-directs the Stanford Center for Induced and Trigger Seismicity. Probably you know very well that he is a researcher focused on seismological studies on active faults and the earthquakes that they generate and physics of the earthquake source. Before being in Stanford, Bill was for nearly 40 years at the USGS, where he was serving USGS as a chief of a branch of seismology, and he was chief scientist of a earthquake hazard team. So Bill received his BS in physics and a master in geophysics from Stanford University and his PhD from MIT. So the talk that Bill will give now is about managing the hazard of induced earthquakes in a changing world.
There we go. Thank you, Stefano, for that very nice introduction, and thanks also to the organizers of this meeting for the opportunity to come here and share with you a North American perspective on the issue of induced seismicity. I should also say that as a past president of the Seismological Society of America, we are really delighted to have this new developing relationship between the ESC and the SSA. And if there are any students in the audience at this early hour this morning, if you're not already SSA members, remember that it's free, so be sure to stop by and see Mary George about that. So let me get started with the talk. I'm going to talk a bit about some of the science, but I also want to cover some of the policy issues with earthquakes, and we'll see how those can be interrelated. In outline, I want to remind everyone at the beginning, as we've seen in the past few days, that induced seismicity is a complex problem. It's one that is really of global extent. I will be focusing primarily on ongoing seismicity in the U.S. Midcontinent, much of which is related to wastewater injection. And then we'll discuss to some degree managing the hazard of injection by looking at 3 case studies. So induced earthquakes, as I mentioned, are a global problem. The figure here from a recent report by the National Research Council identifies places globally where induced earthquakes have occurred. Reservoir-induced seismicity is one that is well known, as is mining seismicity. In Poland, the first seismological network to study this was established early in the 20th century, for example. Geothermal production is an issue that we all appreciate and understand, as is the development of advanced geothermal systems, such as occurred at Basel, Switzerland. Gas storage, as we've heard at this meeting, is also a big issue, as can be reservoir depletion, as we've also been discussing. Enhanced oil recovery is also an issue, particularly in the Permian Basin in the United States, where some strong earthquakes have occurred. CO2 sequestration is an issue that's really now just coming online, and there's an important pilot project underway in Illinois. Hydraulic fracturing, as we heard yesterday from our Canadian colleagues, has been a big issue, particularly in British Columbia and Alberta, whereas in the United States, the main issue is wastewater disposal, and I'll be focusing on that issue primarily during my talk. All of these different means of generating earthquakes are often connected in some way to energy. And we, of course, are in a world in which the energy system is changing rapidly in response to the need to meet the issues of climate change. And so developing resources that are less carbon intensive is one of the strategies that we have, at least as a bridge technology, to get to a more carbon neutral world. In Europe, there's a lot of interesting work going on this problem now. There are the 4 Horizon 2020 projects, of which we've heard some about them in this meeting, and looking at the issue of developing shale resources in Europe. As you can see in this graph, as over time, beginning from the beginning of late 19th century going forward, we've seen a huge increase in the use of coal on a global scale. And of course, coal is about twice as CO2 intensive, say, as natural gas. So one possibility is, in the short term, is exchanging coal as a source of energy, switching gas for coal. From my way of thinking, it is interesting to see what goes on in Europe. It's very different than what we have in the United States. In Europe, typically the state owns the resource, and the usual way of following things here seems to be that you study everything before you do anything. It's quite the opposite in the United States. In the United States, the resource is privately owned, and we seem to do everything before we study anything. So we're going to be looking at cases here in which we typically call ourselves ambulance chasing. We don't get there until things are underway. So we have a little more difficult problem to sometimes piece the story together. In the United States, this shows the locations of the shale basins that have been developed, and we'll be looking at 3 of these, primarily gas here in the eastern United States. This has not been an area where earthquakes have been a major issue, although there have been some. The state of Ohio has been very proactive about dealing with the issue. One of the huge oil basins, the Bakken, primarily in North Dakota, is not one that has had a big issue with induced seismicity, and we think this may be because of the way wastewater is disposed. The big issues are here in this part of the central Midcontinent. We'll be looking at that. I'd also draw your attention to this hockey stick here. This is U.S. oil production. So following the Hubbard curve declining until about 2009, and then we have this big hockey stick. That might look familiar. It looks a whole lot like the hockey stick of cumulative earthquake rate. And in fact, the upturn here is at the same time. So I think there's empirical evidence that there's something going on that links the change in U.S. oil production and the production of earthquakes. And of course, they're correlated very closely in space as well. So I want to say a few words before we get into the details of the talk about the earthquake that occurred last Saturday in Oklahoma, the magnitude 5.6 Pawnee earthquake. It ties the record for the largest injection-induced earthquake that we know of, tying the 2011 earthquake in Oklahoma. It occurred on an unrecognized fault, which is one of our main problems. Unfortunately, there were no fatalities. I think only one person was injured, and minimal damage in the low millions of dollars. This map shows the location of the epicenter, and it shows it on the new USGS map, showing the short-term hazard, a one-year hazard map for the U.S. And the earthquake falls on the edge of the area of high probability. And we can see why that is the case. In this slide, this is a zoom in on part of Oklahoma. This is a 50-kilometer scale here. The red dots here represent earthquakes within the past several years. The bars here represent stress directions that have been determined from hydraulic fracturing or borehole breakouts. The location of the earthquake is here, and I think you can see from this field of stress directions that this fault is very well oriented. It's the fault that appears to be activated here based in these earthquake relocations that Martin Schoenball has provided. Also shown on this graph is the progression by time going forward here. You can see that the earthquake activity is on the edge of the previously active zone. At this point, we think that these earthquakes cannot be tied to a single injection well, but rather the effect of injection on a statewide scale, so a scale of 100 kilometers or more. And we can see that a little bit clearer in this diagram. Again, a 10-kilometer scale here. The earthquake is here. Each of these dots represents a wastewater disposal well. So there's a lot to do to figure out yet how these things are connected. So let's now take a little bit of a look at how this change in the way that we produce petroleum, particularly from unconventional reservoirs, is creating an earthquake problem. So again, here is the hockey stick showing the earthquake, the increase in the earthquake rate beginning in about 2009. This is the time at which the unconventionals really began to get going, primarily in Oklahoma. This diagram is a schematic of the general process. Over here in the corner, we have a conventional oil reservoir. So there's a geologic trap where oil will accumulate over time, and typically these reservoirs have become depleted very quickly. That the water that is produced is often used to sweep more oil out. But at the same time, it's long been known that there were other formations that had a small amount of oil in them, but it was not very productive. So the development of horizontal drilling and very large pumps permitted a new way of producing oil. And basically, they pump everything out of the formation. They drain it and produce a lot of water, a little bit of oil, but they can't put the oil back in the formation. So they typically build a for-purpose disposal well that collects all the oil from the production wells, and then they pipeline it to a disposal well where it is injected. Now, in these areas, the best formation for disposal sits directly on top of basement. And so there is this issue of a hydraulic connection between the injection zone producing a pressure plume which can interact with faults in the basement that are properly oriented for failure. And we think that's the main mechanism here. So to say a little bit more about the actual technology, this is looking at the Hunton group, which is the area of the recent earthquake. In the natural state, the oil and the gas are sort of at the tips of the cracks. They're in the interstitial space, and that by beginning pumping, you can lower the pressure, begin to move this into the fluid system, which you can then extract with a pump. And it's an enormous amount of wastewater, typically 10 to 50 barrels of wastewater for every barrel of oil. You can't put the water back where you took it out because that will stop the flow of the oil. So this is why you have these big fields of hundreds, if not thousands of wells and hundreds of wastewater disposal wells that are all wired together. So it's a very complex system. I think we understand the basics of what's going on. I think the effective stress model is the one that is mostly responsible for the occurrence of these earthquakes. So it isn't the fluid that we're moving it isn't the fluid we're injecting, but it's the pressure that's generated by the injection of the fluid into this filled space. This rise in pressure, of course, reduces the effective normal stress and allows ancient faults, which are critically stressed, to slide. The faults occur on a wide variety of scales. They're found everywhere. So if there is a fault that is critically stressed near the failure point, a small pressure perturbation may find it and generate an earthquake. These ideas are not new, of course. The idea went back to the Denver earthquakes in the 1960s in the United States, and quite remarkably, in 1969, the USGS did an earthquake control experiment working with an oil company. They went to a site in western Colorado, Rangeley, where enhanced oil recovery was generating earthquakes. And the USGS said, gee, could we borrow a few of your wells for about 3 or 4 years? We'd like to make some earthquakes. The company said, sure, go ahead. Hard to imagine this happening today. Anyway, the experiment was very successful. You can see here the occurrence of the earthquakes during the injection period, and then they turned off during backflow. I think one thing that we perhaps have forgotten about this experiment is that this equation was understood in situ before the experiment was conducted. The stress was measured using hydraulic fracturing. The frictional strength of the rocks were measured by Jim Byerly in the laboratory, and the pore pressure modeling was done to determine what would be required to produce these earthquakes. So this was really an important experiment. It's one that we should frankly be thinking about repeating today. And I think one of the things that we should observe here in this picture of injection is that the earthquakes are not only occurring in the injection interval here in the Weber sandstone, but they're also occurring at the basement at distances of several kilometers from the injection well. So we know that this question of pressure being distributed broadly is one that's an important effect. One other important result from Rangeley, this is from the science paper by Rayleigh et al., the cessation of seismic activity within 1 day of the initiation of backflow in the experimental wells in May 1973 established the correlation between fluid pressure and earthquakes beyond a reasonable doubt. These systems respond very quickly to pressure changes, and so we have to think about a fracture-dominated system in which pressure can be communicated to large distances very efficiently and very quickly through fractures rather than through diffusion through a porous medium. Well, there's a lot more that needs to be done to really understand the physics of induced earthquakes than static stress levels in the effective stress law. And here are just a few of my thoughts to think about. We know a lot more about how to start an earthquake than where and when it will stop. And clearly, this is the issue for seismic hazard. We don't care about the small earthquakes. We care about the large earthquake that occurs in the heavy tail of the distribution. We also know very little about stress magnitudes and their variability in space. We tend to think of stress as a homogeneous quantity, but this really can't be right. And I think one of the things that these induced earthquakes are telling us is that by raising pressure by a small amount over a very broad area, we see individual spots lighting up. These are the places that are close to failure, and they tell us something about the stress heterogeneity. We know even less about the permeability structure of the crust and of ancient faults in particular. And so again, I think this is one of the real key issues where we need to we need to think about new ways of really understanding these hydraulic pathways. And as my late colleague Bob Wallace was fond of reminding us, it's not homogeneous stuff we're dealing with. The Earth is a complex place, and we really have to take that into consideration as we build models. So we're now going to take a look at three case studies from the central United States, and I think they'll each illustrate a slightly different part of the problem. One will be the earthquakes that occurred in the Fayetteville Shale play in the state of Arkansas, the Guy Greenbrier earthquakes. We'll also then look at some management issues that occurred in the Mississippi Lime play in southern Kansas. And finally, we'll take a look at some earthquakes that occurred in East Texas near Timpson. So let's begin now by looking at the initial stages of the Guy Greenbrier, Arkansas earthquakes. These are a couple of figures from Steve Horton's paper that appeared in Seismological Research Letters. You can see that during the wastewater injection period, there was a fault that was identified, a fault that was lit up by the injection. This is a case where the regulators and the companies had worked very carefully to find what they thought was a safe spot for injection. The map faults here are poorly oriented in the contemporary stress field. What they didn't know was that there was a deep basement fault that was properly oriented, and this is the fault that was activated. And you can see here that there are a couple of disposal wells that were located near the earthquakes, and the hypothesis, of course, is that by injection, seismicity was triggered on this fault. Earthquakes up to magnitude 4.7 occurred over a distance of about 15 kilometers. The regulators shut down these wells, and the earthquake activity eventually abated. So what we're doing at Stanford is we're looking at the early stages of this, and we'd like to understand how the seismicity evolved was there seismicity occurring before the large wastewater wells were in action, and how did this fault activation begin? So we began by using a template method to find more earthquakes. We found up more than 100 times the number of earthquakes in the standard catalog, lowering the magnitude detection level down to minus 0.8. This is using just a single station, I should mention. And but we have to recognize that the templates may not find all the earthquakes, so we need to do something else. And we're looking for earthquakes that are very close to the noise, so we need some other methods. And so Clara Yoon and her other colleagues at Stanford developed a new method called FAST, fingerprint and similarity thresholding. It's a way of greatly reducing the information content in the seismogram in a way that allows one to identify signals of different types. It's very similar to some of these methods that some of you may know for identifying a song. I mean, you can turn your phone on and ask it to say, what is the name of this song? Well, they're not cross-correlating with every known song in the universe. They're using some very clever ways of data compaction, and that's the same thing that we're doing here. This identified really all the earthquakes that we found by template matching, and I found a few additional ones that we think are going to be important. So I'll show you just some of the results from this work. We found that in the pre-injection period that the earthquakes occurred in a number of clusters. Some of them are on the main fault. The gray dots here represent the catalog earthquakes from later in the sequence. And you can see that there are a couple of places where earthquakes are occurring on this fault, but there are clusters appearing elsewhere. And the question is, why are these earthquakes there? This was quite a surprise to us. Well, they could be associated with other wells. The downward pointing triangles here represent the wastewater injection wells, whereas the upward pointing triangles with the sticks here, these are the horizontal wells. And you can see that there are many wells within this area. So Clara has done a very careful job of understanding where these small swarms of earthquakes were occurring and the timing relationship to the actual to the hydraulic fracturing or stimulation activities. And in general, what we find is most of these clusters are correlated with the fracking operations. Now, these are small earthquakes, none larger than magnitude 1.5, but this was quite a surprise to us to see so much hydraulic fracturing related activity. Earthquakes which are much larger than those that would be normally generated, but smaller than would be of social concern. So just some very quick remarks on this. We think that most of the seismicity of this very small magnitude seismicity appears to be related to hydraulic fracturing. We see that they occur within a short period of time of the initiation of the frac job. We also see that there are earthquakes that occur on the Sky Greenbrier Fault very early in the sequence, and we're still doing work on that. Minor seismicity scattered through the region may be natural seismicity. There is some there. There was an earthquake swarm called the Enola swarm that occurred in the year 2001. And I think in some ways the takeaway here is that abundant microearthquakes during fracking may be a risk factor that we need to think about very seriously before we establish wastewater disposal wells. So now let's briefly look at a project in southern Kansas. This is an area where, again, the development of unconventionals led to a huge increase in the amount of wastewater that was being disposed and followed shortly by earthquake activity. My colleagues at the USGS established a dense seismic network there, so we've been able to follow this sequence in a lot of detail. It's produced some strong earthquakes. This is a shake map for a magnitude 4.3 earthquake, which produced some very large ground motions, 70% of G acceleration at the epicenter and velocities of 12 centimeters per second, enough to do minor damage to some of the brittle buildings in the area. So to address the social concern of many earthquakes being felt, the regulator in Kansas, the Kansas State Corporation Commission, ordered that there would be a reduction in wastewater disposal within these sausage-shaped zones around the earthquake activity. So the earthquakes here are the pink dots. The disposal wells are these little circles with crosses. And they made an order which would reduce the injection for any well that fell within these zones. So let's see how that played out. We've had a year now since the order went into effect. In the zone that produced the magnitude 4.3 earthquake, a statistical test shows that the earthquake rate, cumulative earthquake count before and then after, has a clear change in slope, so that yes, in fact, that reduction had a positive effect on the earthquake rate. Also in this zone here, there's a clear effect. Not in this zone. There seems to be basically a continuation of the earthquake activity at about the same rate. We had a reduction in this zone, but this is a main shock aftershock sequence, so it's not very surprising. This is the largest earthquake occurred here. And it's ambiguous in this zone. What's more concerning is that they did not change the injection rules elsewhere, and we suspect that the operator was taking water that would have gone to these wells and just moved it to other wells. And that results in a significant rate increase in all the area that was not being regulated. Now, since then, the regulator has said we have to reduce the injection in a broader zone. So I think that the thing we've learned by looking at southern Kansas is that, yes, reducing the injection rate can, in fact, have a very positive effect on mitigating the earthquake rate, but don't play whack-a-mole. You've got to take the broader situation into account. You can't allow the company to take water that would have gone one place and put it into another. That will not solve the problem. And this is now what's actually being done in the state of Oklahoma as well, that they're addressing this not on a well-by-well basis, but on really a statewide basis. So the final part that I want to look at is the earthquake sequence that occurred in 2012-2013 in East Texas near the city of Timpson. There were 5 principal earthquakes, the largest magnitude 4.8. You can see some of the damage here to very, very weak structures. These earthquakes, again, generated high accelerations, more than 2/3 G. We published a paper a couple of years ago in JGR which looked at the association between these 2 wastewater wells and the earthquake zone and concluded that they were probably responsible for the earthquakes. This fault is only moderately well aligned within the stress field. It does have a positive stress, but it's not one that would be most likely. So we're still looking at this problem. So more recently, we've decided to look at a couple of additional injection wells, not the 2 wells closest to the earthquakes, but also some wells that are nearby that are also high weight injection wells, and to consider very careful the local geology. Most of this is a section of lower Cretaceous limestones and dolomites, some sandstones and shales. And the injection here is occurring below this red layer here. This is a regionally extensive anhydrite, so a very low permeability formation, which should block fluid flow either up or down across it. And so we have 2 wells injecting below the horizon and 2 wells injecting above the horizon. Now, what was exciting was that my colleague at Arizona State, Manu Sherzai, was able to find deformation data using the ALOS satellite that shows that we are seeing surface deformation related to the injection. And here's a map showing the rate of vertical movement or toward the satellite movement over this period from 2007 to 2011. The west wells and the earthquakes are over here. The east wells are here, and I think you can see that there's a very clear area here that appears to be associated with the east wells that is rising at a rate of about 2 millimeters or so per year. So this is a big number. There are no good ski areas in East Texas, so we know that this is not a long-term geologic process. We think it's very clearly related to the wastewater injection. And one thing I would say here without doing any modeling is you can see that the uplifts is extending to significant distance, at least 8 kilometers from these wells. So the reach of the pressure plume from injection can be substantial. So we've done some modeling of this using a poroelastic formulation to look at the injection at the east wells and the west wells, taking into account this anhydrite in between, which is very low permeability. And in these models, we have the injection histories from all the wells and are able to do this as a forward-looking problem. So we inject and then we have to match the surface deformation. Just to give you a flavor for what this looks like, can I get this to work? Maybe not. So, well, we'll just move ahead. So this shows us the volume strain that is found in this modeling, and you can see that there's very large volume strain related to the shallow injection, but almost no volume strain that is related to the deep injection. We get the opposite picture when we look at the pore pressure. There is a little bit of a pore pressure increase beneath the shallow wells, but the major pore pressure increase is occurring during the deep wells. So again, this anhydrite layer is blocking pressure from propagating downward from these wells, and it's also trapping the injection in these levels, really requiring that it spread laterally and go into basement. So now to look at the correlation between the earthquakes and the injection, this is a little bit complicated figure, but let me walk you through it. The red curve here shows the pore pressure increase in our model at 2 kilometers depth near the deeper western wells. The blue curve here is the pore pressure change at 1 kilometer depth, the injection level near the eastern wells, and then we have a 3 and 4 kilometer level which is near the western wells. And what you can see is that the pressure rises very quickly at shallow depth and then diffuses to a greater depth with time. Also note that the sticks here represent the seismicity. There was an earthquake as early as 2008. It was at a time when pore pressures at very shallow depth had risen substantially, and we'd already gotten about 1 MPa increase in pressure at 3 kilometers depth, which is about where this earthquake occurs. Over time, the earthquake sequence begins in general in about 2010 before really ramping up in 2012, 2013. At this time, injection was cut back drastically at these wells, and as the pressure declines, the earthquake activity abated. So a few takeaway points from this. We feel that it's clear that the uplift was caused by wastewater injection in these shallow wells and detected at substantial distance from the injection point. You might also have noticed that the pressure, the deformation was not circularly symmetric, so it's really being geologically controlled. That's another important point. We also find that the pore pressure increase in the hypocentral zone was on the order of 1 megapascal, so a substantial increase in pressure extending to depth. Declining pressure in the hypocentral zone coincides with the end of the earthquake sequence, which is also quite significant, and suggests that pressure management may be the effective way of managing the earthquake hazard once it has begun. So let me now summarize my talk with just a few thoughts. We've seen from these three cases in which we come late to the game to study the earthquakes in these three different areas of the central United States that pressure management is one of the keys. Understanding the geologic conditions is also critically important. I think one of the lessons from the Timpson earthquake case is that if we can find a way of injecting fluids that has a barrier between the injection zone and the crystalline basement, we are going to be in a much safer condition than we found in Oklahoma and in Arkansas and in Kansas, where the injection was basically going directly into formations that were in direct communication with basement. So there's a lot that needs to be done in coordination with understanding the local geology as well as the hydrogeologic character of the formations that may be accessed. This map shows one assessment of global shale resources. I think you can see they're everywhere. It's hard to imagine that these resources are not going to be tapped at some time in the future. We are the ones who are developing the technology, and I think we have a special responsibility as seismologists who understand the earthquake hazard issue to really learn how to develop best practices. So those can be ones that will be recommended and hopefully followed around the world. And just as a quick reminder, when we have an earthquake of magnitude 5.5 or so in California, not much happens. This is a shake map from an earthquake in 2007 just on the edge of Silicon Valley. No fatalities, no injuries, no damage. The 2011 Prague, Oklahoma earthquake, it really is pronounced Prague. Magnitude 5.7, same size, no fatalities fortunately, some injuries, $10 million or so in insured losses. And we can compare that with the 1986 San Salvador earthquake, same size, magnitude 5.7, 1,500 fatalities. So what really matters here is the exposure and the fragility of the infrastructure that is being exposed to the earthquakes. I think we can solve this problem. We've made great progress, and I think it's going to be an exciting time for the field going forward. We need to think and solve these problems locally so that we can act on them globally. So with that, thank you very much for your attention.